So I'll start by introducing our speaker today, Dr. Laura Tolos. She's a tenured researcher at the Institute of Space Sciences in Barcelona, Spain. She is going to give this 30th Theoretical Physics Colloquium in the series. She got her PhD at the University of Barcelona in 2003. After that, she had several postdoctoral positions as an Alexander von Humboldt Fellow at Goethe University in Frankfurt, as a postdoc at GSI for a year, and then as a junior fellow at Frankfurt Institute for Advanced Studies between 2006 and 2008. After that, she had a tenure-track assistant professor position as a Rosalind Franklin Fellow at the University of Groningen. From 2010 to 2017, she was Ramon and Cajal researcher at the Institute of Space Sciences in Barcelona. Then she was a Heisenberg Fellow at the Institute for Theoretical Physics in Frankfurt until this year. And since 2020, she is a tenure researcher at the Institute of Space Sciences. She has interests and great expertise in strangeness, in stars, heavy hadrons under extreme conditions, equation of state of neutron star matter, transport coefficients in superfluid neutron stars, and dark matter in compact stars. And with that, I'll give the microphone to Laura.
Okay, thank you very much for the invitation, Igor, and also for the nice introduction. So yes, a long time since I finished my PhD. So yeah, so what I would like to talk today is about the strangeness. So as Igor mentioned, is one of the topics that I've been working in the past. And well, the title is really general. It's strangeness in nuclei and neutron stars. And this is actually the title of one review we wrote with Laura Fabietti for this journal, the Progress in Particle and Nuclear Physics. And actually, well, you know, strangeness could mean anything, you know, with a strange degree of freedom. So basically, in this review, we discuss kaon physics, we discuss also phi, we discuss also hyperons. And actually, the talk today is, I thought, you know, to concentrate on one of the topics, and it's going to be, oh, sorry, I went too fast, hyperons. So basically, I'm going to discuss a bit of what we know nowadays from the theoretical point of view, relating it with experimental physics as well, on hyperon physics. So basically, I'm mentioning hyperons in nuclei as hyperons in experimental facilities. And the second half of the talk will be to relate, you know, to neutron stars and how strangeness in the form of hyperons appears. So basically, this is the reason of these two figures here. This I will mention now. So this is the, you probably know, this is the nuclei chart where you have here the stable nuclei. But then you can see here, you know, this extra axis with a strange degree of freedom. And actually these new nuclei, which I call hypernuclei, which are being experimentally studied in the past. So with that, let's move on up to the outline of the talk. So first, to introduce what are hyperons and where we can find them. So I already mentioned it a couple of seconds ago. Then I will move to hypernuclear and hyperon interaction. So basically how hyperons interact with nucleus and also with themselves or with other kind of particles with strangeness. And then I will try, you know, to explain you very briefly. So, but a bit about hypernuclei and a few things that we know experimentally and theoretically, and then move to hyperons in matter, so as to pave the way to discuss neutron stars. And well, present and future is just my point of view on in general on hyperon physics. So hyperons, I mean, all of you, I mean, you're particle physicists or nuclear physicists, so you know that. Just that you know that the baryon containing one or more strange quark is meant, I mean, the definition would be a hyperon. This is how we call hyperons. And here you have a table with different hyperon going to the lightest one, which is the lambda, up to the omega. And you can see here that the content, the quark content and the mass. And well, this is usually the classification that you have, you know, that having the octet of baryons, where you have the hyperons, the S-1, where you have the lambdas and the sigmas, the cascades, and then you also have the decuplet, where you have the, let's say the vector, not the vectors, but the excited, let's say the star ones, you know, the excited, the sigma stars, the cascade stars, the omegas and the deltas for the case of strangeness equals 0. So, I mean, this is just for people who didn't actually know what a hyperon is, but probably most of you know. So where you can find them? So basically you can find them on Earth, but basically you have to produce them. So one way is doing through scattering, which is a difficult task. But one area, let's say, of people working to understand strangeness and to why is important strangeness in matter and in strangeness in particular interacting with other degrees of freedom like up and down, is because we can have the so-called hypernucleus. Okay, so the idea here is that you have a nucleus and you bombard this nucleus, this target, and then some, you know, it is possible to create, given the energy of the beam, the bombarding beam, so just to create these hyperons, and those link to the hypernucleus. Okay, and then you have a new set of nucleus which have a different spectroscopy, as you can see. Well, that you cannot see, but you know, they have a different spectroscopy and different properties that people are interested. So actually, again, I'm moving to this chart here. You have this, you know, neutron, proton number and neutron number. So you have here the stable nuclei. Here they are unstable one created through these R and S processes, for example, in stars. But what I'm interested is going, you know, in this zeta axis, where you have a strangeness equal -1 or a strangeness -2. And then here you have a lambda, for example, binding with the nucleus, or as a strangeness -2 or 2 lambdas binding with the nucleus, or cascades, for example. Okay. So, and why is this interesting? Well, because it sets a new spectroscopy in the sense that you have new nuclei, and then you can try to understand the different levels, you know, in this new nuclei. And also, of course, in order to understand how they are built, you get information on the strong and also on the weak interaction. Okay, so how those hypernuclei then will decay. Okay, so this is related with one possible scenario that you find on Earth, but you also, of course, you can have the hypothesis, because this is just up to now we don't know for sure, that you might have this strange degree of freedom in neutron stars. And in particular, one of the species that people discuss inside the nucleus of a star will be these hyperons. So I mark them with this blob here, like the sigma, these lambdas, these cascades. Of course, you can have some other, you know, let's say models, or you might think of other hypotheses of what you have inside in the core of a neutron star. And these, of course, could also be not hyperons, but could be bosons, it could be kaons, it could be pions. This is the H-type baryon. I mean, I'm not going to discuss anything about that, but you can also have it. Or you can forget about hadrons, okay? You can forget about that, and you could have basically the confined matter in different phases, if you have superconductivity or superfluidity. So this is, as I said, I mean, different possibilities, and one of them is to have hyperons. And depending on what you have there in the inside of the core of a neutron star, the properties of the neutron star will change. So this is kind of an introduction, you know, to the problem, let's say. But in order, you know, to understand, you have to start from the basics. So basically try to see what we can extract from experiments and what can we extract from theory for the hyperon, nucleon, and hyperon interactions. So here I put, let's say, the experimental information. So let's say we have a scarce information on hyperon nucleon scattering data. You can imagine, because the hyperons have a short lifetime, for example, the lambda 10 to the -10 seconds. So it's difficult to really have, you know, beams of hyperons. So basically you don't have actually beams. So you usually have kaons, and then you collide them with targets and you get hyperons. And then, well, this means that you have really actually low density beam fluxes, and really difficult to create this scattering with hyperons and nucleus. So what I'm saying by scarce is that if compared to nucleon data on scattering data, you might have like 5,000, even more, you know, data, let's say events for energy in the lab below 350 MeV. Above, you know that you enter in this hard core of the nucleon, and then there is not scattering information. And compared to that, you have like what, around like 50 points on Hyperon nucleon, and very regarding lambda nucleus or sigma nucleus, sorry, sigma nucleon and lambda nucleon. Even cascade nucleon is very few events. So as you see, I mean, there is really not so much information from the experimental point of view on the scattering. You have information on hypernuclei. So you have no more than 40 lambda hypernuclei. So this gives you already information that the interaction with lambda and nucleons is attractive. Otherwise, you cannot create these hypernuclei. You have also a few lambda hypernuclei, but the interaction actually is very weak. I mean, the information, it seems to be around what we say, you know, for large nuclei, around saturation, the density of large nuclei, around saturation density. We're talking about less than 1 MeV, so really very little attraction. There is also information on a few lambda hypernuclei, for example, on carbon. Also gives you information on attraction there. And then actually there's no evidence of sigma hypernuclei. So there is information on sigma minus atoms. So sigma minus occupying, you know, electronic, let's say, levels, but not really nuclei, okay, nuclear levels. So this gives us maybe an information that we are having here a repulsive interaction. So the theoretical approaches to understand this Hyperon nucleon and Hyperon are moving, let's say, from the approaches that most of them start with, you know, nucleon interaction and extend that to strangeness. So basically, there is this old way, let's say, of having, you know, interaction of nucleon that's still working, and it's still, you know, we have to still take it into account, which is building the Hyperon nucleon and Hyperon from the point of view of meson exchange models. So as the base is nucleon, and basically you impose SU3 symmetries, and then with the data that you have, you fit the free parameters that you might have. Then you have the chiral effective theory. So this is really a strong group in Jülich, Bonn, and Munich, working on that. So basically trying to build the Hyperon nucleon and Hyperon to leading order, next to leading order, let's say, you know, starting again from what they know nucleon. And then you have other ways of approaching, like quark model potentials that are based on constituent quark models and try to build the interaction between hadrons, between baryons. Then you also have this Bill-OK approach. I'm not sure if I mean, this is an old work, let's say of 2006, old, yeah, 14 years now. Like the idea is to have this universal effective low momentum in potential as in the nucleon, but using renormalization group techniques. So I'm not sure nowadays, I mean, people are still working on these renormalization group techniques to understand the nucleon interaction. I don't think there has been much progress there lately on Hyperon nucleon, but maybe I'm wrong. So anyway, and then of course lattice, the idea of people working on lattice by the whole QCD collaboration in Japan and the NPLC QCD collaboration in the States and in Spain actually, and also I think in Germany there are some people there as well. Also try to construct, you know, these interactions in the lattice. In this talk, actually, I'm going to mention, you know, what a bit of what has been done here in the meson exchange models and in the chiral effective approach. And here I just show you, for example, the two big groups, okay, in the meson exchange model. So you have the Nijmegen group and the Jülich group. So here you have actually the people who build those interactions. Some of them also involved, as you can see, Heidenbauer, for example, is one of the ones that also involved in the chiral effective models, approaches, let's say. And well, the Nijmegen is based on the nucleon, and then the idea is that you build, you know, you implement SU3 symmetry in order to get your coefficients, your vertices. The way of building the meson exchange model is the exchange of pseudoscalar, vector, and scalar nonets. So And well, the idea, to regularize is what is called through Gaussian form factors. And as compared with Jülich, you can imagine they also have their nucleon-nucleon interaction. So both interactions, of course, the nucleon-nucleon reproduce all the scattering data, okay? The only problem, of course, is what happens when you enter in this hardcore and when you enter in the short range, okay? Then there's a lot of difference there. And here you also have exchanges of single mesons, but you also have higher order processes like multiple exchange of mesons. Here they use also the spin symmetry, to relate to the hyperon nucleon vertices, and well, a different way of, let's say, regularizing or taking out, let's say, when you enter into the short range, okay, these form factors. So here are some examples. This is for the lambda nucleon and sigma nucleon scattering. So basically the idea is that you solve with this potential, this two-body potential, which is this hyperon nucleon, you solve the Liebman-Schwinger equation. And then, for example, here is just an example of the Jülich 2004, which is the blue line here, with the scattering data at the time of the paper. This paper is, I believe, from 2013. So you can see here, well, just to look now for the blue line here. So this is lambda proton. This is sigma minus proton going to lambda neutron. And well, you can see here, sigma minus proton going sigma zero neutron. You can see that here, well, the data is more or less going, the theoretical model is going through the data. Now, I just wanted to point out that compared to the scattering data, there is new results, what is called femtoscopy, for example. This is like analyzing this correlation function, which is given here. So basically, my understanding is that you have, the baryon-baryon pair. You have two baryons there, and you analyze them in the same collision. So the correlated baryon-baryon pairs. And then you divide by what is called here the mix. So basically it's with different collisions. And then you see whether, as a function, of what is called the reduced relative momenta in the baryon system, in the two baryon rest frame. And the idea here is that experimentally they can extract this data. So you see that one here. And this correlation function actually is related with the scattering length and with the effective range of the interaction that you theoretically can extract. And then you can calculate these correlation functions, okay, theoretically, and see how it compares. So this is a new way actually of getting more information on the interaction, on the hypernuclear interaction. There is now, of course, the chiral effective field theory, where the idea is to, of course, to have a systematic analysis, which is not present when you use meson exchange models, because sometimes it's difficult to have a systematic analysis. Which diagrams are most important? Well, these in the meson exchange picture usually are the ones which are the single ones, okay? But they don't have this power counting that you have in effective field theories, okay? And also the idea is, as I said, the idea is to do a systematic way of building up the interaction and knowing your uncertainties and your theoretical errors, which in this case are basically analyzed through the change in the cutoff. Okay, so there's maybe other sources of uncertainties that are actually not analyzing these error bars that they give. Okay, and the idea here again, you have the octet of baryons, and the idea is to construct the leading order and next to leading order, which in this power counting means that at leading order you will have these contact interactions and the one or single exchanges of mesons. And then in the next to leading order, you will have contact terms which have derivatives, two derivatives. And then here you have higher order exchanges, two meson exchanges, okay? So with that, and now I'm going back again to the same picture that I show you, is now that you can look, into the leading order and next to leading order. So this is the computations by the Jülich-Bonn-Munich collaboration on one of the first calculations, okay, because it has been improved. I will show maybe a bit later more, but still, you can see here, this is again the green one is, for example, lambda proton, so this would be here. Here you have a resonance, okay, you have a bound state I don't recall, I think it's, yeah, lambda kind excited state. This is what the model sees. The scattering is difficult actually to see this pump here, but this you obtain. And then the next to leading order, you can see that it deviates a bit, okay? So basically, here is just, you will see it maybe better in the case of this cascade scattering nucleons. So basically here you only have what the information that they use, okay? For building these interactions, you need also some experimental information to get out the vertices, okay? And here basically they have some limits, okay, on the scattering data. So basically the idea is that you can see again, this is the next to, sorry, this is the leading order and this is the next to leading order. So you would expect actually some convergence, but here actually there's a different prescription. So the leading order really tries to fit to this scattering data, while the next to leading order, they are doing kind of a couple of different approximations. So there is here not this, or they didn't expect to have this convergence. So, but anyway, you can see what is the data that, I mean, the results that they are obtaining, and of course, compared to the data, you can say anything, right? I mean, at least with that one, okay? This is, sorry, I forgot to say, this is cascade proton going to cascade proton, okay? Now, femtoscopy again is giving you new information. So here you have proton cascade minus. So basically it's just to compare with this old data here, just to compare, well, old 2006, okay? So here you have the results, very recent results on these correlation functions, okay? So this is the experimental data. And I mean, this is the analysis done for this ALICE in proton lead collision at 5.02 TeV. And you see here, I believe this is actually using the calculation done with in lattice with whole QCD. Okay, so using the potentials. So from whole QCD, from the lattice QCD, basically here they can extract the potential and then compute these correlation functions. And you can see here what it seems, what the theory, or let's say the lattice simulation is giving. So let's now move to hypernuclei so that you have a bit of an idea of how they are obtained, how they are produced. So there is, of course, all data on emulsion experiments, but here I'm showing you, let's say, in the past maybe 30, 40 years. Yeah. Information on how to extract, lambda hypernuclei through 3 different ways. So for example, through a strangeness exchange. So basically here you have these reactions where you have, for example, a neutron and a K minus, right? And then the final state is a pi minus lambda. And then here you have this exchange of strangeness, okay? So the strangeness from the kaon is moving to the strangeness of the lambda, okay? This is why it's called a strangeness exchange. And the reactions, that are being done like this, like you have actually a beam of kaons, okay, going against your nuclei like carbon, and then you end up having a pion and your hypernuclei. So you can see here experiments at CERN and BNL, Keck and Finuda at Daphne. So this is one way that they are producing these lambda hypernuclei. There is also associated production. So the associated production is basically that you have a pion beam, and then you collide with, again, a nuclei, and then you get K plus and lambda. So you create strangeness, associated strangeness. So strangeness S bar, which goes with a kaon, and S with a lambda. And actually compared to this strangeness exchange, those are, there is low density beams in this kind of a strange reaction as compared to those beams here, okay? Sorry, I want to say that the production is less, not that the beam intensity. You have more beam intensity with the pions, which compensates somehow the production rate, okay, of this kind of this associated production. Then you also have electroproduction. Electroproduction, exactly. So basically, you through a virtual photon, so that you create in this electron E prime. So basically, this virtual photon collides with the proton, and you get a K plus and a hypernuclei. Okay. So these are different ways actually in different experiments. Here, this one is for JLab or MAMIC in Germany, where you generate these carbons with a 1 lambda, okay? Carbon, sorry, these nuclei with 1 lambda. There is also creation of double hypernuclei. This is maybe a bit more involved. For example, the PANDA experiment, the idea is to have an antiproton beam that collides with the nucleus, carbon, for example, and then you create pairs of anti-cascade and cascade. And this cascade is captured by a secondary target. And then you have this kind of conversions, cascade proton going to lambda lambda. And then this lambda lambda, you know, are linked, bind with the nucleus. And of course, at the end, they decay. Okay. So in this way, you can have this Bohr. Yeah, it's called Bohr, right? Lambda lambda. And you also, I mean, this is a way, let's say, of producing lambda hypernuclei. And you can also have, through reactions, you know, these kind of reactions actually can also give information on cascade hypernuclei. So actually you could create, for example, this beryllium with a cascade minus through reactions like that. K minus going to a proton, and then a cascade binds with the beryllium, and then you get a K plus outside. Okay, so this is a way of having cascade hypernuclei. For example, at Keck in Japan, they are also doing this. So with that information, the idea is that you extend your axis to the, you know, into this vertical axis. So here you have the different reactions. Here it says stop because usually when you have a kaon beam, usually you try to do it as low as possible. So stopped, basically low. And then you create, you know, all these lambda hypernuclei are here. Then you double lambda hypernuclei. And as I said, I mean, the interesting is, you know, to understand the spectroscopy, to understand the properties of those nuclei, to get information on the interaction. And this is, for example, I mean, this is an example on the binding of the lambda hypernuclei and how we, you know, the people doing neutron stars get information or why this famous minus 30 MeV or minus 28 MeV at saturation density comes from, that people are using in neutron stars. Okay, just to have this information. So basically, this is different hypernuclei, different levels of S, P, D, F, G. And then this is for different as a function of the mass number. And then the idea is that you can see these continuous lines are basically what is called a single particle model that reproduces well these levels, okay, as a function of the mass number. And actually this 30 MeV you can see here that is in the large nuclei, okay, that you're getting this binding energy that's saturating at this value of minus 30 MeV for large nuclei, okay? There is also, this is, I mean, if you want more information, there is this review by Abraham Gal and collaborators of 2016. He's an expert on hypernuclei. There is also something really interesting nowadays that people are somehow has revived, in my opinion, which is this hypertriton lifetime puzzle. This hypertriton is this, I mean, this hydrogen with lambda, okay? And the fact that you have information, these are different experiments, okay, on the lifetime, ranging from 64 to the latest Alice data, very last data on this hypertriton lifetime. And what is the puzzle? The fact that this hypertriton binding energy is small, it will mean, you know, that the lambda wave function doesn't change much. So you would expect that the lambda, the lifetime of this object, will be similar to the lifetime of the lambda. And it turns out that you can see, I mean, this is the lifetime of the lambda, this continuous black line. So somehow the experiments, you know, are tending to have a lower value. Okay, so they are, for example, the star data, the latest star data is here, the Alice data is here. So somehow the puzzle is here. You know, you would expect to have a similar lifetime, but it seems the observation is giving less than the lifetime of the lambda. So where is the solution? So this is something that the theory, and here you have different ways of models, you know, trying to they put it in a continuous line, okay, just to see, but just that you know that the predictions on the lifetime, okay? So this is two examples, okay? There is a spectroscopy, there is more information, and for example, decays, weak decay of the hypernuclei. This is also another field that people are working. But I'm going actually now to move to matter and maybe go a bit faster, so if I want to make it to neutron stars. So that just see that in order to have neutron stars, you actually have high dense matter. You have beyond this saturation density. The saturation density is this density in average in this large nuclei. It means they related to the average density between two nucleons, okay? So it is this 0.16 Fermi to the -3, 0.15. So you go beyond that, or you think, I mean, those objects are very compact. And then you need to extend your models to this high density. And this is what people have been doing. For example, I'm showing you from the the chiral effective model and the Jülich model. So here you have the prediction. This is again the Jülich model for the lambda hyperon potential as a function of the energy, the Fermi energy, the density. So saturation density will be around this -30. This is saturation density. And you can see here, you know, the difference between the leading order or the next to leading order for the lambda or the sigma. So for the lambda, you see this attraction here. For the sigma, you see a repulsion as a function of the density. So let's say the lambda has to be, well, I mean, the data, what is giving us, as I showed, this lambda hypernuclei, this binding energy of around -27 to -30. But higher densities, we don't know. And the sigma is something that people, you know, are still debating because there are still people thinking that we might have attraction. But as I said, it doesn't seem that sigma hypernuclei are existing. So then it's probably repulsive, the interaction. Here there is just an improvement from the chiral effective model in symmetric matter, in the sense that is improving the theoretical calculation. Maybe this is not so important, but just that you see that they are doing not only symmetric matter, but neutron matter, okay? And then it's important also the isospin dependence on the sigma interaction, for example. This is again the potential as a function of the density, and here for the lambda and the 3 sigmas. And here is, this is a function of the density, and this is at 0 momenta. Actually, yeah, I mean, this is as a function of the momenta. Sorry, I forgot. This is at density saturation for different densities as a function of the momenta, and this is as a function of the density at 0 momenta, okay? Anyway, so just that show you that people are trying really to get to neutron matter. For the cascade as well. So the cascade, I mean, the cascade is here, and really you see a problem, you know, with the leading order and the next to leading order here as a function of the density, the Fermi momenta. The small binding that they are obtaining, whether it seems experimentally, it's a bit more. But again, there is not much information on the scattering, okay, which is one of the informations in order to constrain the theoretical approach. And the interesting thing here is that the 3-body forces, because now people are also trying to implement 3-body forces because they might be important, in particular to analyze non-relativistic many-body approaches that are applied afterwards for neutron stars. Here, the way is, you know, doing many-body calculations using density-dependent interactions. So basically, you do a 2-body density-dependent interaction. And what you see here, basically, that I want to point out is in neutron matter, which is this part here, you see the potential again as a function of the density, and then you see the repulsion that you observe with these models at higher densities. And this is something that I will discuss briefly later, which is related with the Hyperon puzzle. The fact that if you have hyperons, these I'm just introducing the concept, you will have a softer equation of state, you will have less mass, and then you will be in contradiction with experimental data. So somehow, this I will come back, but the idea here is that if there is repulsion, then those hyperons appear, but very late, and they will not affect, okay? So this is, I will mention that later. So I think I have, what, like 20 minutes, a bit less? or 20, yeah?
Something like that.
Okay, so then once I introduce a bit of what hyperons and nuclei, we know, I mean a bit, okay? I mean, as I said, there is more information on hypernuclear, on spectroscopy, on weak decays and so on. I just choose a couple of things. I move to neutron stars. And neutron stars are, for those who doesn't know, I mean, this is an introductory slide. They are forming corpuscular supernova explosions observed as pulsars. They are referred to objects between 1 and 2 times the mass of the sun, radius of 10 to 12 kilometers. This is a big question mark. What is the radius? Densities, if you calculate the mass divided by the volume, you can see that the densities, average densities are high. So you might get up to 10 times saturation density, which translates into 10 to the saturation density in grams per centimeter cubic. This is mass density. This is baryonic density. So this is number of particles. This is just the mass density. Magnetic fields can range to very low magnetic fields to very high magnetic fields, and then you have the field, what they are called magnetars. Temperatures, depending on the evolution, of course, because these objects are cooling once they are creating supernova. So they are around, 10 to, I don't know, 10 to 8, 10 to 9 will be the average, I would say. But this is actually cold because 10 to 10 Kelvin is 1 MeV. So if you compare with the Fermi energy, these are cold objects. And you have observations. You have observations of masses, the radius. Maybe now I could take out this question mark, but there's still not much information. Gravitational waves, cooling. And this is kind of a summary of observations. So you have masses. You have actually interesting observations of masses of 2 solar masses. These are highlighted here. And also with this value of 2019 of 214. Why is important? Because you will see that theoretical models sometimes are difficult to get these 2 solar masses. I mean, really got a model that gets to 2 solar masses. The radius before NICER, they were like a range between, depending on the analysis, basically because it was extracted from the atmosphere, the X-ray emission of the atmosphere. So there was a lot of uncertainties there. So you could range maybe around from 8 to 16 kilometers, depending on the analysis, depending, of course, on what you think of the atmosphere, on the magnetic fields, on the distance to the object. So there was a lot of difficulties, okay, for those analyses. Now we have this from the last year, NICER measurements. There are 2 analyses that, as far as I could find, around 13 kilometers, okay? There is also information on cooling. So you have here these cooling curves. I just took one analysis where you have the effective temperature as a function of the age of the star. And then you have all these models and the observations here. And of course, you have the gravitational waves, that you have these binary mergers and the information that you can extract out, how these objects are in this merging phase, how these objects are being, not modified, but, like the shape is changing, so what is called, they extract the information on this tidal deformability, on this deformability of these objects. And this is actually linked to the equation of state, okay? And so somehow you can get information. Well, here there is a famous plot you've probably seen of the 2 tidal deformabilities of the 2 objects, okay? And these are different analyses with different equations of state. And this would be, let's say, the confident, in this area, what the gravitational wave. This is the analysis of the 170817. There is also a more recent one, the 25th of April, 2019. I think here there's still, at least the theory papers, a lot of debate whether one of the stars is a black hole or is a neutron star. I heard talks in August where the people working on gravitational waves, they really believe there are 2 neutron stars. Okay, there. Okay, so with that information, let's look up the mass and radius. So basically the idea here, you have hydrostatic equilibrium. So you have the pressure of the matter that you have inside, which is preventing the collapse, okay? So gravity against pressure. And this is what is telling basically the way that we solve these equations, which are telling us that, and telling which is the mass and the radius of those objects, okay? So of course, for having the pressure, you have to guess, let's say, or think of what you can have inside the object and which kind of matter do you have there in order to get your equation of state, okay? So your energy density as a function of the particle density, or your pressure as a particle density, or the pressure as a function of the energy density. So these are thermodynamic quantities that your model can get, and then with that you can get the mass and radius. And here you see one plot of mass and radius with some boundaries. This is excluded and this other region are excluded because of limits of general relativity, because of causality. And also this is using the highest rotated star up to that moment known, which also forbids that region here, because otherwise the object, basically is called this mass shedding limit, where you have the centrifugal force will not compensate, or let's say it will disrupt the stars, okay? You cannot go farther than that. And then the allowed region would be that area here with observation of 2 solar masses here. And then you have here your models. The blue ones are hadron models, nucleon models, while the green ones are strange quark matter, okay? So basically models where you have basically in the whole star, it's made of the confined matter, okay? And of course, you start seeing here that there's a lot of models ranging radius from 7 to 15 kilometers. Some of them reach these 2 solar masses, some of them not. But the main problem here is the constraint on the radius, okay? Because as I said, there was up to very recent, not really an information of one, let's say object with a certain radius. And then you could see anything. All of these models could get to 2 solar masses, but still the radius in that model, for example, would be almost 15 kilometers, when in which this one will be 12 kilometers, okay? So, I believe, and NICER hopefully will give us some more information, and also the future collaboration with Europe and China, the XTP, which the idea would be, I will mention later, to really get, objects that we have the mass, with of course some uncertainty, to really pin down and find and observe the radius, okay? And really get information on the radius. Okay. Now, if we just think of nuclear matter, we just don't think, we just think of nucleons. The equation of state has been given, in lots of approaches. In a lot of models. So I divided them into groups: microscopic ab initio approaches or phenomenological approaches. The difference between them is basically the way to approach a problem, in the sense that here you start with your 2-body or 3-body interaction, and then you put the many body corrections on top of that, okay? So you have variational methods, you have quantum Monte Carlo, you have coupled cluster expansion, you have what they are called diagrammatic, which is this Bruckner-Hartree-Fock that maybe some of you have heard. Then more relativistic, Dirac-Bruckner-Hartree-Fock, renormalization group methods, lattice. And the advantage of this is that you have a systematic addition of higher order contributions, but the problem, for example, is up to where we can add, okay? Let's say chiral effective model with this renormalization group, similarity renormalization groups techniques, you can ask up to which density we believe our model, okay? Maybe it's saturation, 2 times saturation density. What are the densities actually in the star? So they are higher. So this is the advantage of the phenomenological approaches, in the sense that you have density-dependent functionals, and those are adjusted to things that are known, nuclear observables, observations. So I'm talking about Skirm models, I'm talking about relativistic mean field models, relativistic Hartree-Fock, liquid drop models, Thomas Fermi statistical models. The problem here is that, they are not systematic, but they are applicable to higher densities. Okay, so, and with that, you can think, okay, let's think if we have hyperons, okay, because the mass of the lambda is not so different as the nucleon, okay, the lambda is one around 1,115 MeV. The nucleon is 940. So you might have at some point densities which is more favorable to have lambdas and to have nucleons. And this is actually seen through what is the dominated equilibrium relations are given by this beta equilibrium. So this is the kind of reactions that are happening in neutron stars that determine the equilibrium, okay? This is beta decay and this is electron capture when you only have, I'm missing some bar here, sorry, antineutrino. But the idea is it's possible to have more exotic degrees of freedom if, because of the high value of the density at the center and because of the chemical potentials that actually are the ones dominating, explaining those reactions, okay? So what I meant is that actually you can have these kind of reactions where you have a neutron, for example, neutron going to neutron and lambda, or a proton electron instead of going to a neutron to have it at a lambda. And the idea is that those reactions are actually understood in terms of the chemical potentials, okay? So basically, for this reaction to happen, then the chemical potential of the lambda has to be equal to the chemical potential of the neutron, okay? And in this way is also the same, because actually the chemical of the proton potential of the proton plus the chemical potential of the electron will give you the lambda. And actually this sum is equal to the chemical potential of the neutron, okay? So the idea here is actually summarized here. So these are the conditions for a lambda to appear or a sigma minus to appear, okay? And the fact is that if this chemical potential of the neutron is increasing with density, this is what you see here, okay? This is as a function of the density. It can happen, for example, that at some point it goes above the mass of the lambda, okay? And then you will start having lambdas because it's more favorable to have a lambda than to increase the neutron chemical potential, okay? And this is actually what you see here. This is particle fractions as a function of the coordinate of the going towards the center of the star. So initially, if you have neutrons, at some point, actually, I will mention the sigma, you have appearance of lambdas, and then the neutrons start decaying. Actually, what you see here is that the sigmas appear first, even if the mass of the sigma is higher, because the relation is also not only because of charge neutrality, you also need the electron. And it turns out that it's easier, as you can see here, that the chemical potential of the neutron plus the chemical potential of the electron reaches the sigma mass. So it happens before, okay? And this is the reason why you see here the sigmas appearing first and the kink on changing the particle fraction of the neutrons, okay? So my message here is that it might be energetically more favorable to have sigmas, lambdas, instead of nucleons as you go more inside, farther inside the neutron star, okay? But what is the consequence of that? The consequence is that if you have an equation of state, which is this pressure here as a function of the energy density, and then you put hyperons, the pressure lowers. This you can understand because of what is called the release of the Fermi sea, the energy of the Fermi sea. So basically, you have a new particle, so you have a new set of Fermi energy levels, and then you start populating the lowest, okay, of the lambda. So therefore, the whole system, it's kind of a release of the Fermi energy of the system, okay? So this is happening in the softening. If the softening happens, you can imagine you have the pressure against gravity, okay? It's in Spanish, actually, gravedad, okay. Pressure as gravity. So basically, your maximum mass is lowered, okay? So this is what is showing here, the mass as a function of the density towards the center. And you see here that this is actually with nucleons and leptons, and this is just with nucleons with hyperons. And then the whole thing lowers. So what happens? You have a strong softening of the equation of state, and the maximum mass lowers, and this gives you problems with the two solar mass observations. And this is called the Hyperon puzzle. Solutions to that? Well, the solutions are several. I mean, the idea is that it is energetically probable that you have hyperons, but then it induces a softening of the neutrons of the equation of state, and then the maximum masses are lower than expected, or let's say as compared to the ones with only nucleons. So the idea would be, or to have a stiffer interaction with hyperons, hyperon nucleon, hyperon that we don't know, to have something which is stiffer, or the three body forces as well, to implement them, or even the idea is to push the appearance of lambdas, okay, or sigmas. The idea is to push them to higher densities, so they will appear, but at higher densities, so the softening will be not so strong, and you could still reach the two solar masses, okay? Or you could go in another way, you know, like having dark matter in your object, or even not, you know, having modified gravity theories. Like you don't solve actually what I show you, the TOV equations, but you solve more complicated because you have other, you know, modified gravity. Okay, and with that, I'm almost done. So I just now for the future, I just wanted to show you a bit more detail. This plot that I show you as the mass of the radius, okay, where you have here different models. This continuous line is just for nucleons. Then you have hyperons, which is another model with hyperons, which is not the same in the nucleonic part. Otherwise, they will be similar in the low density part. Then you have also, I didn't mention hybrids. This is hybrid model. You have a king here. This means that you have first hadrons and then you have quark matter. Or you might only have quark matter. This is these continuous lines. And those bands here are from analysis using, for example, that one is based on effective field theory and constraints, observational constraints on the two solar masses. And those, and this band here, which is more like violet, well, I don't know the color actually, this, yeah, violet, whatever. It is using not only this effective field theory constraints, but also in a very high dense regime, using perturbative QCD constraints, and then trying also observational constraints of two solar masses, okay? So of course you can see, as I showed you before with these models, the range of possibilities with the radius. And the idea, of course, is that these blobs here is what observations might give us, okay? So nicer, we already have one around 13 for a 1.4, so it will be somewhere here, okay? So the idea is also, for example, this EXTP, to get this information. How they do that? A way of doing that is analyzing what these profiles, these pulse profiles. So this is the idea of looking at one neutron star and then some hotspot, and then you know, these pulses are rotating, and then you have a fluctuation, okay, of the luminosity, and this wave, let's say, and this amplitude, this profile depends strongly on the compactness of the object, okay? So if you have know the mass, then you will extract the radius out of that, okay? This is a one way through what is called this pulse profile modeling, okay? But of course, I didn't mention much, but we also have now this multi-messenger astronomy. We have all these binary, well, we have this binary, two binary mergers of neutron stars where you can get information on the equation of state. So, and then just my light slide, I just wanted to give you a bit of an overview. I mean, I didn't went too much detail. I just wanted to say that there's a lot of experimental, observational, and theoretical effort in hyperon physics in nuclei and neutron stars. We need for that actually the knowledge on hyperon nucleon and hyperon interactions, especially in hypernuclear physics and also in neutron stars. Neutron stars help us to understand to go with hyperons to even higher densities. And I believe the future goes not only with the particle and nuclear experiments that are being performed and planned, but also, I guess, going through, you know, this X-ray analysis, astronomy, and also this multi-messenger astronomy. So I think that's it. So, yeah.
Okay,
So
thank you very much. Thank you very much for a very nice presentation. We will start with the questions now. Okay. David, you are the first.
Okay, David, I just stopped sharing. I stopped. Oh, maybe you need my slides. Okay, we'll go back.
Yeah.
Oh, okay, so thank you very much for a very nice talk. Laura, I have a following question.
Yeah.
I had discussions with Tom Reichen and also with Yasu Yamamoto.
Yeah.
And they have quite some interesting work, maybe you know it, from 2017 in PhysRevC is a paper. They argue there is a multi-Pomeron exchange, a short distance, which they introduce as a many particle force.
Yes.
And they tested in oxygen, there are oxygen-oxygen collisions, and they have the angular dependence of the differential cross-section, where when they just use, for instance, argon V18 potential or extended soft core, they cannot quite describe the large angle scattering.
Okay.
So this repulsive short-range force helps them to lie perfectly on the data. When they then use this multi-Pomeron interaction for nuclear or neutron star meta calculations, this gives them a solution of the Hyperon puzzle.
Okay, yes. I mean, yeah. I mean, as you know, I mean, the question is how to make equation of state stiffer. I mean, if you have in the short range, like really more repulsive interaction, then this will, of course, stiffer your equation of state.
It is kind of a clever solution because also it allows to have a better description of the nuclear ground state even. So they get them from the calculation with this many particle force. They get very nice description of the saturation and also the solution of the Hyperon puzzle. A nice, now my question really to you is, if so, then should one consider such a result for mass radius curve, which corresponds to this work, as the minimal possible radius from purely hadronic equations of state? Anyway, when you have the well-known Akmal-Pandari-Pandar-Ravenhall equation of state, which is so much used also in astrophysics in particular, they don't have hyperons. So in principle, one should not use it at all. Right?
Okay, my point of view, I mean, is that I don't know exactly which densities are testing this hydrogen-hydrogen. So we also have to be careful which densities are they testing their interaction, okay? So if you tell me that they give me information up to 2 saturation density or 3, then, I mean, it's good. The only thing, of course, then have to see the extrapolation to higher densities, okay? Because at the end, also you have to be, I mean, we have to know, okay, our experiment is giving us, right, this density range, and this density range, then we can really trust, okay, I mean, if we explain, of course, the experimental data, right? I mean, but also we have to know, I mean, I don't, depending on the I mean, two solar mass observations, for example, you can get maybe 4 times. I don't know, depending on how stiff your equation of state. If it's stiffer, then it's less the density, right? So, I mean, my point of view is, yes, you have to use, I don't know if to use it as a benchmark, up to where we can use it. I mean, the point is to see up to where we can use this benchmark. And as you said, Akmal Pandari Panda, this is one of the ones that everybody uses, no hyperons. I guess because in the low density, it's really describing nuclear matter. And so, but as you said, I mean,
supernovas, you barely reach nuclear matter density, maybe a little more, no? And then you don't excite you don't expect to excite hyperons there. Okay. But for the neutron star problem, it is probably dangerous, yeah. But you know, you have yourself, you showed this little graph from Morgan Fortin with the radii, and you have shown the very small radii also of this work of Rutledge and Guyot, which in the community is practically abundant, yeah. So
so
these are 2 small radii.
Exactly, this analysis of Fortin, exactly, of Morgan. So this one here, you mean,
So an interesting question which relates to this is, what is the smallest radii from a purely hadronic picture? In other words, when NICER will bring now smaller radii, then whatever was a realistic nuclear model you could describe, then this should be a good hint to exotic matter in the interior, right?
Yes. Okay. The point is, okay, is always also discussing, you know, with Alessandro Drago. We would like to have not here in the middle, okay? Because in the middle, hadronic models can get to 12, okay? So relativistic mean field models, my experience, for example, with those is telling me that I can get to 12, okay? I can get in that range, okay?
Yeah.
So if I have a result around 13 from NICER, then I'm probably not discriminating much the equations. So what I would like to have is something or very low or very high, okay? And then I think this will be a breakthrough in the sense of really discriminating models, okay? You asked me, hadronic models, where you can make it. As far as I've seen, I mean, you cannot maybe lower to 9. I have not seen, or maybe I'm wrong, but I would say 12, 11. So this will be the ones, I mean, and at those, right, we are talking about masses usually of around 1.4. So here usually don't have hyperons yet. Okay?
No, the real point is now
Yes.
NICER is measuring since 1.5 years the
Yes.
Cromarty pulsar, so the one at 2.1 something plus minus.
Yes. Okay.
And the radius will be released somewhere soon.
Okay.
And so the point is, what shall be the radius at 2 solar mass?
Yes.
Theory.
Okay. Yes. Yes.
And
I mean,
my point would be APR gives 11 kilometers or even a bit smaller.
Mhm.
And this should not be taken as a realistic hadronic model. Although you find it everywhere, it should be abandoned for such questions. I
think, David, we will abandon it when we see the data, not until then.
Yeah, we will see.
So anyway, next question. Let's go to Ephraim.
Yes, thanks, Laura, for the interesting talk. Can you talk a little more about the three-body interaction? If there is a way already to get from there some effective kind of interaction that can be used in the Lagrangian, or?
Well, as far as I know, I mean, I share again. I mean, I should have not share again. Okay, here. I go back. I mean, all these. Okay. I here. Yeah. I mean, my comment here is, for example, what people have been doing in the chiral effective models is implementing these three-body forces, but up to now they appear at this next to leading order. So basically, they do some density-dependent two-body. Okay, so basically they solve. If this is your question for the details, they solve the Liebman-Schwinger with this also two-body density interaction. For what is the effect of these three-body forces? Now, I mean, this is where you're going your question in the neutron stars. This is your So what is going this is actually there's a paper I didn't mention of Weise, and but also where they see that because they have these three-body forces, as I see here, for example, that you get you have a repulsion, extra repulsion, okay, on your interaction, and this makes the lambda appear much later than if you don't have these three-body forces, okay, because somehow you're putting some repulsion, then you are modifying the mass, right? You can think that, and then this equilibrium with the chemical potentials makes the lambdas appear much later. Okay, and then because of that, you might still get these two solar masses, for example. Okay, so this will be an effect of the three-body forces that people are exploring, not only in chiral effective models, okay, but also in these meson exchange models. They also implement these three-body forces somehow in the Liebman-Schwinger. I mean, it's in this diagrammatic, what is called this Bethe-Goldstone expansion with three-body forces. And then they also observe this repulsive effect, okay? So the effect of the three-body forces, what people are seeing is an extra repulsion into the properties, for example, of these hyperons. And this extra repulsion, what is helping is in towards solving this hyperon puzzle, okay? I don't know if this was your question.
Yeah, great question. And the coping constant that they are using there, from where they get it?
Sorry?
The coupling constants.
These coupling constants. Okay, I have to look. These are this called the CEF parameters. I have to see exactly where the experimental data some of them are getting. For example, for neutron stars, there is actually there are some diagrams here that did not appear. I mean, they only appears, I think, it's called the CE and the CD. So basically, I think they only these two terms in neutron matter, okay? In neutron matter. So I have to look. I don't remember. I mean, they extract some of these parameters out of some experimental data, but I can have a look. I don't remember.
Experimental data.
I think so. I think so.
Okay.
There is this paper. Those papers are Heidenbauer and Meissner, and actually I used. I mean, for the hyperons. Not sure. I don't think they have. For nucleon, there is information on that. Okay. On hyperon, I don't think so. Okay. I was mentioning only data on nucleon, on 3 nucleons. Okay.
Okay. Thank you.
Okay. Next question is Boris Tomasic.
Hey, Laura. Yeah.
Hi,
So I also have a question to this plot that you have on the next to last slide, actually. And so it's an outsider question who always gets updated. Yes, that's it. So there are no data points, no observations on that plot. And I was wondering, does it mean that all those models, all those curves are accepted by the current data, or can you put some constraints already on what is known today?
Okay. Yes. I mean, this plot was taken from this EXCP paper. Okay. Where we, assuming that we have these blobs, then how it would look like. So the current data would be, observation of 2 solar masses. So it would be lines here, which we don't know yet the radius, okay, of these objects. And then you also have the 1.4. There's also very famous. The idea is to mass and radius, okay, data. So masses we have of 2 solar masses, at least we have 3 that I know, which very small errors that are around 2. Okay, and then you have the nicer one. The nicer one is again, where did I put it here? The nicer one is here. For a mass of 1.3, 1.4, depending on the analysis, you have radius of 12 plus, well, 12, almost 13, plus minus 1. So in this plot, it would be something like 13, and then you go here, okay? So you will have something, but 1 kilometer. So it means from here to here, okay? So it's still maybe a bit large uncertainty, okay? What they are claiming, or the idea will be to have a 5% error bar, okay? So right now is what? It's a 10%, right? So if it's 12, 10, around 10, a bit more, okay? A bit less. So the new measurement will be around here, maybe here down, like this, okay? I would say we have to wait, of course, to have more mass and radius, because right now, actually, you could say you only have 1, okay? And as David said, if you have 2 solar masses, then you're constraining all these models that are really having difficulties in getting to 2 solar masses, okay? And if you have a radius here, then you know that you will have something, maybe, I mean, you will have to have a model that goes through this region here, okay? So now it's masses. So you have 2 solar masses, you have 1.4 for sure. So the constraints will be 2 solar masses and this nicer event that should be lying between 12 and 14 kilometers for a mass of 1.3, 1.4.
But sorry, Laura, we have the tidal deformability from the W 170817, which tells that the radius at 1.5 should not be larger than 13.5 kilometers. So your strange quark matter curve is excluded.
It's already being too far. Okay, if you use the tidal deformability information, then you will be lying somewhere in that region, as David said, okay? But you also, I mean, those objects are also between 1.8 and 1.1. I think they were in that region here. Okay, if you also think here, multi-messenger. I was only showing mass and radius observations. You also have something here. Yes. Yes.
Okay.
Thank you.
Okay, let's go to the next question from the Bharati Chatterjee.
Yeah.
Hi, Laura. Really nice talk. Thank you. So I have a comment for David Blaschke, but I will first probably ask you the question. So how can we put a limit on the maximum repulsion of hyperons from experiments? Is there a way to do this? Because,
okay, experiments, what I was showing, you know, on hypernuclei, these are, I mean, I was talking to you about large nucleus and the densities that we were discussing is saturation density. So if you really want repulsion for higher densities, I don't think hypernuclei is the way. I don't know. That's why I was asking maybe David, you know, this oxygen, which are the densities they are testing. Okay. So experiments, I don't think, I mean, at these high densities it's difficult to get, you know, to know any experimental data as far as I know, okay, on this, on how to constrain, okay, this equation of state actually at the end of the day for neutron stars. So these, as I said, here are testing really, and here even lower densities. So really you are testing regions that this repulsion at high densities are not tested. You could think of heavy ions, right? But there's always this, this discussion whether those systems are really symmetric systems, as in some of those nuclei as well, okay? And also the temperatures, because as I said, these neutron stars are cold. So at the end of the day, you also have to be cautious, okay, in extracting. So these high densities, I think it's difficult to test it at 0 temperature and high densities in an experiment, okay? Maybe somebody has a solution, but I don't think it's common knowledge, okay, how to test that there.
You also showed the particle fraction where you said the sigma minus appears first, but I think this is very dependent on the model, right? Like, for example, if you put HAL QCD potentials, or if you take an RMF model, you will have a lambda first. So.
Well, depends. Depends on the RMF, okay? Really depends. Yeah. Because here, I mean, this is an old picture, but I mean, if you just think of non-interacting particles, okay, because you don't know the interaction basically, then you definitely see that the sigmas appear before the lambdas, okay, because of the masses, okay? If you just think of the masses. Now, if you put repulsion on the sigmas, attraction on the lambdas, then they start getting closer, okay? And then in some models might lambda appear before sigmas, okay? In some others, still sigmas appear. So, I mean, I did, and of course, as anybody, right? I mean, just this sigma minus interaction repulsive at saturation density, the lambda attractive of -30, and still, as I recall correctly, my sigmas were still appearing before, okay? But as you said, I mean, there are relativistic mean field models that also get lambdas before, because maybe the repulsion at higher densities, because now we are already testing densities, not at saturation, but at really higher densities, okay? When they appear here, these sigmas, I mean, those still, in that model, maybe it still is 0.2. You're still at saturation, 2 times saturation density. The lambda's not, okay? So maybe the lambdas are really, you know, depends on the model. So you have to see how your model does when they appear, at which densities are you studying and how repulsive or attractive your potential is, okay? But as a first step, if you don't think there is any repulsion, I would say, if you just think that there are masses, with very simple models, usually the sigma appears before the lambda.
I wanted to make just one comment about what David Blaschke just said about the Pomeron exchange. So with the in the review paper that I wrote with Isaac Vidania, so there we also mentioned these Pomeron exchanges. But if I remember correctly, in that case, the nucleonic if you consider only the nucleonic forces, then the masses were really low. And if you consider universal forces for all baryons, then the masses were above 2 solar masses. So there was still an open question as to whether all the baryons can be treated universally in the multi-boron exchange. But I don't have any updates about this. So I don't know if David was talking about something more recent. I have to look it up as well.
So I was referring to a paper from 2017, PhysRevC, with Yamamoto, Togashi.
Yes, from Yamamoto. Yeah, exactly. That was the group.
And
yeah,
Riken.
okay. Okay. Thank you so much.
Okay. Any other questions from the audience before we will wrap this up? Actually, I did have one question that I didn't get a chance to ask myself. You mentioned about this EXTP experiment, and
Yes.
my understanding is that there is some similarity to the NICER. So what exactly is this EXTP? I'm not quite sure I understand.
Yeah, I mean, this EXTP it means enhanced X-ray timing pulse polarimetry telescope. So what I know is that there are different ways of through this X-ray, basically through this rotation. I mean, it's called X-ray timing. Okay, so basically, for example, these pulsations I was mentioning, that they can extract given the mass by some other observations, the radius, for example. Okay, as I was mentioning here, because of this pulse profiling modeling. There is also other ways, I think, that they want to extract information of the mass. There is also using this, how is it called? This is this mass shedding, this spin, this pulsation. This I don't know much the details. Now, what is the difference between NICER and EXTP? I believe probably the sensitivity, but I don't know. I have to check exactly what the actual differences are on one and then the other.
Superficially, they seem to be similar, right?
Yeah, they seem pretty similar. I only have to probably, which is the sensitivity or what is the. I have to look into the technical details. To be honest, I don't know exactly.
Okay, sounds good. So if there are no more questions,
Hi.
No, go ahead.
Yes, I have a question because there were comments made by people who are very expert, and I would simply like to know if you could go back one slide.
Yes.
No, back again to the okay. So from your previous slide,
yeah,
as you increase the chemical potential,
yeah,
you're going to produce strange particles, right? You have to.
Yeah. Yeah.
So what do you need to get, say, 2 solar mass stars? I mean, I know this was answered several ways, but
what do I need? Well, what I need, one way of approaching is that the hyperons appear late. Okay, for example, this is the idea.
Could you go back one slide and show me?
Yeah. So what I want to say, okay. The idea.
How about the sigmas?
Yeah.
Just the hyperon?
Yeah, just because here is just a model. Okay, the idea would be that the sigma, the chemical potential of the sigma goes like that and crosses this line really far in density. Okay, so if this sigma is not here, I mean, starting on the mass, but somehow is really flat, and this goes, smoother, okay, like this, and they meet at a higher density, then the sigmas will appear later. Okay, so, but the idea would be somehow to avoid this decrease of the chemical potential, to avoid this fast decrease. So basically putting some repulsion, okay, to that object.
Specifically a 2-body, a 3-body?
A 2-body. You could do it a 2-body.
Between sigma and nucleon.
Yes, exactly.
So you need sigma nucleon bigger than nucleon.
Not necessarily. Not necessarily. No. I mean, with 30 MeV, you can make them appear later. Okay. So, but the point is, because this meets, I'm sorry, maybe if this meets at high densities, your chemical potential at this density, it will not be this 30 MeV at repulsion I was mentioning, but maybe your model is giving you 100 MeV, okay? So it's a balance, you know, of how the two-body interaction changes your effective mass, okay, somehow. Even at the level of two-body, at those densities, okay? Do you follow me or?
No, I follow. I'm just trying to understand why I've heard this many times. If you have a lot of repulsion for the strange particles, you don't have a problem. They never condense, which I didn't understand. But my question is more, why should the repulsion for a baryon with one strange quark be bigger than that with no strange quarks?
No, it's not necessarily. No. Okay, I don't think it's necessary to have that. But you, for example, for the sigmas, it's not only nucleons that you have, you also have electrons, okay? So somehow maybe it's more clear for the lambdas, okay? You should compare if you want, the effective mass of the neutron with the lambda, okay? And how they change with density, okay? So if at certain point, the effective mass of the nucleon, you know, at certain density is larger than the effective mass of the lambda, then you will have lambdas.
Yeah.
But this, so, I mean, the sigmas is maybe you have the electrons, so maybe it confuses a bit more, but the lambdas, I mean, the idea is that somehow that it's not exactly the effective mass, it's effective mass, I'm thinking of, well, the repulsion or attraction, okay, that you have on top of your mass, okay, which could be scalar or vector, whatever. So it's as compared to the nucleon, but at those densities, we don't know, okay? The point is whether they meet, I mean, I know what's happening at saturation density, but I don't know what's happening at 4 times saturation density, okay? So, I mean, I think...
Maybe I can once more point out this, this multi-pomeron, this many particle force is short range repulsion is really clever because it is not, so we would maybe in terms of hardcore repulsion, we would think of quark exchange or quark Pauli blocking. Then indeed the Pauli blocking by a lambda should be less than between nucleons because just only the identical particles block, and the Pauli blocking does not help very much here for the hyperons, but this multi-pomeron is gluonic in nature, and therefore it is not dependent on the flavor so much, or independent on the flavor. Right? And therefore it blocks also the hyperons as it blocks the nucleons at short distances. Maybe this gives a little hint.
Yeah, I mean, of course, I mean, at those densities, I mean, you enter in this short range, right? And then you might forget also about having hadrons, okay? And then having quarks and gluons, and then you have other things there, okay? So, but if you concentrate on a picture of these densities, you're definitely entering this short range region, okay? If you think of nucleons, like really getting closer together at those densities, then you have this repulsive effect, okay? But you also might wonder if it's really the degree of freedom, okay? Here we assume it is the degree of freedom, okay? So somehow, this is the region as David said, you know, you're getting too close and this is the Pauli, this is this repulsion there, okay? But as I said, I mean, we don't have control on that. I mean, we don't have control on that, and then you just guessing.
If I can add my 5 cents, basically we cannot allow the equation of state to become too soft, no matter what it is.
Yeah,
and
I mean,
that's the only thing you could really say. The rest,
I mean, they always this here is okay. Your hyperons appear late, yes, or somehow also if you have your nucleons which are really stiff, and then you allow hyperons. But then you have to see whether hyperons appear. I mean, it's always, if it's too stiff, then hyperons might appear fast and then it will soften a lot, okay? So it's a balance of, it should be stiff with nucleons, but it shouldn't be too stiff that hyperons appear, but then hyperons should somehow be also have a repulsive interaction. So, you know, it's a bit of playing, you know, with this, but at the moment it's just guessing at those densities.
if I may, is Veronica here? If I may make a comment to your comment. You have to be careful when you say just stiff or just soft, because we know from tidal deformability calculations that the equation of state must be soft at low intermediate densities. So we needed to be stiff at high densities. So it's very complicated in that sense.
Yeah, okay, that's right. I mean, you needed to, for example, for having radius of 1.4, radius of small radius, you needed to be soft. But for the around, around, at least in the relativistic mean fields, right, Veronica, you need to have a soft equation that gives you radius around 11 kilometers, 12 kilometers. But then you need it to be stiff to get to 2 solar masses. So, but it's also a different density region where you're analyzing your equation of state, okay? So you might still have some soft at saturation or 2 times saturation density, but then you really need to stiffen up in order to get to the 2 solar masses, okay? So it's true. So my point was just that it's softening. When you have hyperons, it softens, okay? So it really is the effect. Now, what you need is for radius, I mean, in order to have small radius and also to have, there is experimental information on what is called, I forgot this radius of neutron matter with respect to proton, this ratio. I forgot the name now. Anyway, so there's some experimental data also that is also constraining you this region of around saturation and 2 times saturation. So the equation shouldn't be too stiff at the beginning. Okay, so yeah, Veronica is right. So we have to be also careful where we say it's stiff or soft.
Okay, sounds good. Any last minute questions before we wrap this up? I don't see anything. We had a lovely discussion already, so I would like to use this opportunity to thank our speaker, Laura Tolos, for this very nice presentation. I think everybody enjoyed the presentation itself, as well as the questions. So